All right, let's look at how to get the triple vector identity now that we've learned some more stuff about the interior product, which is really just great stuff on its own if you want to learn more about differential forms. But here will be kind of a small payoff for that. So first of all, I have to elaborate on the last part of the last video. I put in a correction, an annotation. I got the order wrong. I just forgot to write it in the right order. There's a subtlety about the order when you express the cross product in terms of the interior product. It's actually IA of star B tilde is B cross A tilde, or in other words, minus A cross B tilde. So let's just check that. If A is E1 and B is E3, for example, star E3 just means star of DZ, and that's dx dy. If you IE1 that, then it hits the dx. That's where they actually match and gives you 1, and then the dy is left over. When you pass it through with the derivation identity, then it doesn't do anything on the dy, so you just get dy left over. And we've seen that calculation before. Well, that's the one-form version of E2, the second basis vector, and that's E2 is E3 cross E1, not E1 cross E3, because again, cyclic order. Okay, and of course it's that tilde. So that's it in the right order. If you're wondering why I'm using E1, E2, and E3 instead of IJ and K, I could use IJ and K, but it'd be weird to say I sub I guess. I think that's why I'm not using IJ and K. So now that we've got that, it's kind of cool that this seemingly obscure identity, the vector triple product identity, actually is going to be equivalent to the most basic identity about the interior product, which is why I feel like this is an interesting way to talk about the identity. So here it is. We just take the vector triple product, and we got to convert that to a form to use form language. We could convert it to a 2-form or a 1-form. Either way would work. I'm going to use the simpler way, which is convert it to a 1-form. Okay, so now that is minus interior product, just using what we had before, of the 2-form version of, what's this? B cross C. So I'm just unpacking it one step at a time. Okay. But now I want to translate that into form language. And that's exactly the 2-form version of the cross product is exactly just the wedge product. Okay. So here we're using this fact that I emphasized in the last video that depending on how we want to translate vectors to forms, 1 forms or 2 forms, or on the input side and on the output side, there's these two very different translations. And when it all comes out in the wash, what we discover is that the 1-form translation of the vector triple product is exactly, just up to this little minus sign, just a combination of one exterior product, which is this cross, and one interior product, which is this cross. And so that's what I was alluding to by saying that in this point of view, these crosses really are operating in very different ways and almost in different worlds. And in the third view, I'm going to talk about another way to see why that's not such a bad way to think about it. Okay. In fact, in fact, a physicist, there's such a thing as called an axial vector. And they would say, yeah, B cross C is actually an axial vector. It doesn't really deserve to be a real vector. Let me talk about that just briefly. Remember, the one funky thing you need to know to calculate a cross product is the right-hand rule. That's equivalent to having a fixed orientation on three-dimensional space. So this guy, the answer to this, depending on using the right-hand rule. If you put it in a mirror, you'll get a different answer. Notice what we're doing here. 2 crosses, you use the right-hand rule twice or use the left-hand rule twice, you'll get the same answer because the switches will cancel out. And so that suggests that, in fact, this first cross has a different flavor from the combination. And that's a bit of a hint of what's going on here. Okay, so now I'm just going to use the derivation identity. That's IA of B tilde, so minus sign on the outside. Okay, and then this guy, IA acts on the first thing and leaves the second alone, just like a derivative. Then minus, because this is just a 1-form, and we've switched it past that and incurring a minus sign, IAC tilde. Okay, so that's just going to switch the sign, okay, and then in addition to switching these, or switch the order of these guys, so, and what is it? IA tilde, or IA of C tilde, that's a 1-form being eaten by, or a vector being eaten by a 1-form. It's just the dot product. So it's just B times the dot product of A and C. So that was this really crucial thing, that the interior product combined with the tilde is just a fancy way to write the dot product. And then this is going to be the same deal. This is just A dot B times the vector C. Oh, tilde. Okay. Now this is as a one form, okay? But so the tilde of the triple product is, this is just a number, this is just a number. This is clearly just the tilde of number A dot C times vector. It doesn't matter the order here because it's just a number. I can put it on either side. A dot B vector C. And we're done. So that is the punchline for this view, this one page basically. That converting this cross to the two-form version or the exterior product version and this to the interior product version, it tells us that when we combine those, we expect something nice to happen. And these interior products that happen here turn into the dot product. Okay? So in a sense, these dot products are sort of the same operation as this cross product that we started with, not really realizing, but just expressed on differential forms of different degrees. Well, that's funky. Okay? So I want to take this a little further, though. If you just wanted to see that punchline, you can stop. But there's a nice way to make some of this stuff more symmetrical and to give you a hint of what comes beyond it. Let's define the exterior product by a vector on a form. So this is going to be an epsilon instead of an iota. So notice this is very parallel to the iota sub u alpha notation. It's just going to be take that vector, translate it into a one form in the usual way, the tilde, and just wedge it in. Okay? So notice this increases degree, or raises degree, by 1. That's opposed to the I, which lowers the degree by 1. And there's sort of a beautiful duality between these operations. Okay? So there's a whole bunch of relationships between all these guys. I, star, the volume form, wedge, and epsilon. Okay? So I'm just going to give you a small piece of that, of a big story. Okay? So, and in fact, let me do it in the style that I often do, which is actually suggesting that you do a fair amount of the work. Okay? Show, this is a pretty easy one, that just like with the eyes, the exterior product operation, let's put an alpha here. If you do it in the opposite order, you get the opposite answer. Okay, you might want to pause before I give away kind of why that's true. Why is it true? It's just wedging in, and wedging is antisymmetrical. Okay, this is just u tilde wedge v tilde wedge alpha, which is definitely, because they're one forms. It's the basic thing about one form algebra, or algebra forms, is that odd forms anticommute with each other. Okay, so as a corollary, what is the epsilon u operator squared? If I do this twice and it's the same vector, just wedging in u twice, oh, that just dies. That's going to be 0. Notice how that's very, very parallel. Both of these are very, very parallel to IU. The same things are true for IU. In particular, that squares to 0, and it's, of course, very parallel to d squared equals 0. So we have all these operators that, if you try to do them twice, they just die. It's not interesting to do them twice. But that's the world of antisymmetric quantities. Okay. Second one is nice little fact, kind of related to what we were doing with the big identity. What if you, let's see, here's 2a. A very easy one is EU EV times 1. 1 is a great thing to operate on with the epsilons because this is degree 0. And then if we put the epsilons in, we start building stuff of more interesting, bigger degrees, presumably more interesting. Well, you can pause again if you want to know what that is, but it's just u wedge v wedge 1, u tilde rather, wedge v tilde wedge 1. So it's just u tilde wedge v tilde. Okay. Not that interesting, but it's interesting that it's dual to this fact, IU IV of the volume form. Okay. That is the dual, the Hodge star rather, of v tilde wedge u tilde. Okay. Notice the order switch. This is very much this is a generalization of what I was talking about with the order switch, the one that I messed up on in the last video. Okay. And so what we're seeing is that the epsilons coming from the bottom of the forms just recreate the wedge product. The i's, if you go from the top form, the volume form, it is the star of the wedge product. So that's this upside, that's kind of this correspondence, that star kind of turns epsilons into i's, basically. There's a way to say that very precisely, but I don't think I'm going to focus on it. Okay. And then, so this one, I'll leave to you. This is true in any Rn. So all this stuff in the last few minutes is really, what's interesting about it is it's true in any Rn. We're not in R3 anymore. We do have to have a dot product to make the tilde make sense. We do have to have an orientation to make sure we know which dv we're going to use. But it makes sense in any Rn. Okay. Now, the claim is that if I put these together, instead of taking an antisymmetric combination of e's with e's or epsilons with epsilons, exterior products with each other or interior products with each other, what if you combine them with each other, one of each? Okay, that's, yeah, okay. What if I combine them in an antisymmetric combination? That's called an anti-commutator. The claim is, so this all acting on alpha is, what's it going to be? What kind of degree is it going to be? If this is a p form, that's going to lower it, then raise it, or raise it, then lower it. Oh, it should actually just be a p form. And the cool thing is that it's just a scalar multiple of what you started with, and that scalar multiple is the dot product of the two vectors that you acted on with it. Okay, this is really, really useful, and I'm going to continue right there with the next video.